before we talk about Lab 10. Okay, right, so let's talk about Lab 10. So first of all, next week, the Tuesday, we will skip Lab 11 and doing Lab 12. Okay, so when you do the pre-lab, make sure you're doing the pre-lab for Lab 11. Okay, I mean Lab 12. And so for this week is Lab 10, which is about filters. Okay, so it is a very important lab for final projects. Okay, so the I think probably half or more than half of the circuit on the final project is about the filters. Okay, so make sure you understand this week's lab. Okay, so first of all, why we need filters? Okay, so for example, in your cell phone, there are definitely will be filters, okay, because like in the environment surrounding us, there are many different frequencies signal, but your cell phone only want like one or a range of frequency. So you need or the cell phone need a filter to filter out the frequency or the signal it doesn't want and let the signal it wanted received by the cell phone. Okay, so that's a basic function of the filter. It filter out the frequency it doesn't want. Okay. Before we talk about the circuit of filter, there are a couple things you want to know first. First is the impedance. Okay, so we mentioned this before. The impedance for the capacitor and the inductor is as is equal to these two equation, and these two equation is related to the frequency. Okay, and another thing is the unit called decibel. Okay, so like in lab 8, you study about op amp. Okay, so when we talk about the gain of op amp is just voltage divided by voltage. Okay, voltage divided voltage. So that's a voltage gain. Sometimes we don't use voltage gain. We will use decibel, but it's a similar thing because you can use these two equations to transfer from voltage gain to decibel. Okay, and the gain for the unit for the decibel is dB. Okay, and we will use this unit for this week's lab. Okay, and for okay, and there's another important parameter here is negative 3 dB, which is also usually called cutoff point or cutoff frequency when the output is at negative 3 dB. That is when the output is equal to 0.707 input. Okay, so that's the negative 3 dB, and that's where the cutoff frequency of the filter. Okay, let's see anything else. Okay. Okay, then it's a frequency response plot. Okay, or we call the magnitude response plot. So that's a plot which you can see the x-axis is frequency. Let's go to the example. Okay, let's use this as the example. So x-axis is a frequency. The y-axis is a magnitude response of the circuit. Okay, so which means you can see how the circuit work at different frequency. Okay, so for example, this circuit right here is a low pass filter. Well, so it's we can see directly from the name, we want the frequency, the low frequency signal pass through the filter. So that's why you can see here at low frequency, the magnitude is equal to 1. Okay, so that means the output is equal to input. Okay, so this is the gain of the filter. Or if you use the decimal scale, is 1 is equal to 0 dB. Okay, and then when the frequency increase, okay, you will see the magnitude start to decrease. Okay, so that's how the filter, low pass filter works, right? So the low frequency, the signal can go through the filter. When the frequency go too high, the high frequency signal will block by the filter. Okay, so that's a low pass filter. And make sure you also check this example, because this example show how to do the basic transfer function calculation by using the impedance equation. Okay. All right. Okay, and of course there are different kind of filters. Okay, there's a low pass filter and a high pass filter, and also there are band pass filter and also band reject filter. Okay. All right, so let's jump into the tasks. Okay, so task 1 and task 2 is pretty similar. The task 1 is the low pass filter, and the pass 2 is high pass filter, and the required cutoff frequency is exactly the same, and also they are going to use the same equation to calculate the RC value. So let's say task 1. Before you're going to build this circuit, you need to calculate the RC value according to the cutoff frequency equation for the low pass filter, and also the cutoff frequency is given in here. Okay, so after you calculate the value for RC, you can build this circuit on the breadboard, and then you can for the input, you're going to give a 1 volt VPP sine wave. Okay, and then you're going to measure both input and output by using oscilloscope. Okay, so for step 5, you're going to plot the gain and phase response plot. So that's a magnitude response I mentioned. The easier way to do this in the AD2 is you can use a function called network. Okay. So if you open your waveform, there is a network function. So this automatically sweep the frequency. So for example, right here, according to the requirement, you want to switch from 10 Hertz to 100 kHz. So that's 10 Hertz to 100 kHz. Okay, so you can change whatever the frequency range you want. And here is asking you how many points per decade it want to measure. Okay, so usually we do at least 20 or even 13 works. More points here make your plot more accuracy, but that will make the running time slower. Okay, but at least you want to do 20 here. Okay. And then here is the wave chain. Okay, that's control what's the input. Okay, so here the requirement of way in is 1 VPP, which means the amplitude will be 0.5. Okay, 0.5 volt. All right. Then there are other things you can do is you can change the range of the plot. Okay, make it make the plot looks better. Okay, so you can change the range of x-axis and even also the y-axis. Okay, after you get the plot, okay, so you can use this cursor. Okay, if you click this in here, use this cursor to measure the -3 dB point. Okay, so ideally, after you plot this on the waveform, you will see something looks like this in the main-tailed response plot. Okay, so that's 0 dB. At beginning, that should be 0 dB. And then when the frequency increase, the magnitude decrease. Okay, at when it's reach at -3 dB point. Okay, so that should be this frequency right here. Okay, this cross point should be something around this value. Okay, 23.873 hertz. Okay. So you're going to use the cursor I mentioned to measure this point. Okay, then that's step 4 and step 5. Okay, then for the step number 6, it's asking you to measure the -3 dB point by adjust the frequency. Okay, so in this step, you will not need to use the function, the network. Okay, what you need to do is you want to back to the function generator, okay, or the wave generator, and the oscilloscope. Okay, so you're going to use the function generator to provide the input and the scope to measure the input and output. Okay, so you want to make your wave gen to this frequency right here. Okay, and then measure the input and output. When it's hitting the -3 dB point, the input and output will be exactly this ratio. Okay, so what you need to do is you want to manually adjust the frequency of your function generator or wave generator until the input and output amplitude is exactly this ratio. So that will be the exact -3 dB point. Okay, so should be very close to this value. Right, so that's task 1. The task 2 is pretty similar. You're going to repeat the same process, and you just change the position of RC, so make it high pass filter. Okay, and make sure when you do this two task, when you take a screenshot, so the screenshot will be okay, so for example, task 1, step number 5, the screenshot will be a screenshot of network. Okay, or you can plot the data in the other software. The most easier way to do this is just plot it in network, and make sure the screenshot in the screenshot you do have the cursor measure the -3 dB point. Okay. All right, so that's task 1 and task 2. Okay, then task 3 is the RLC band reject filter. Let's see. Okay, one thing I want to mention again is this is a circuit diagram for the task 1, task 2. Okay, so you're going to add the input is function generator or wave generator, and also you're going to use channel 1 to measure the input and use channel 2 to measure the output. Okay. Okay, then task number 3 is the RLC band reject filter. Okay, so the value of the RLC is already given, so you just need to build this circuit on the breadboard. Okay, so the input is as the input of the resistor is connected to the resistor, which you will also use a function generator as the input. And the output is the voltage across the inductor and the capacitor. Okay. One thing you need to do here is, although it's mentioned you want to sweep the frequency from 10 Hz to 100 kHz, but 100 kHz is not enough for this plot. Okay, so you want to at least sweep until 1 megahertz. Okay, so make sure you remember this in the when you do this task. Okay, so after you do the measurement, okay, after you plot this in the network, you will see something looks like this. Okay, so the x-axis is frequency and y-axis is magnetic response. So as we mentioned, this is a band reject filter. So that's why you see this little dip here. So the frequency around this range is going to reject by this filter, and the lower frequency and higher frequency will pass through this filter. Okay, so if you didn't sweep until 1 megahertz, okay, the plot will cut off at somewhere here, so you are not able to see the right part of the response plot. Okay, and then after you get this plot, you're going to measure the resonance frequency, the bandwidth, and also compute the Q factor. So first of all, where is the resonance frequency? It's the lowest point of this magnetic response. Okay, this point right here, that's the resonance frequency. So you can use the cursor I mentioned to measure what's the measured resonance frequency. And then question number 5 is asking the bandwidth. Okay, so for the low pass filter, okay, let's draw this right here. The cutoff frequency is at the negative 3 dB point. Okay, so which is right here. So that's a cutoff frequency. And for this plot right here, you see there are 2 cutoff frequency. One is right here, one is right here, because there is a decreasing and a increasing. Okay, so the difference of these 2 cutoff frequency, that will be the bandwidth. Okay. And then after you get the bandwidth and also the resonance frequency, you can use this equation to calculate the Q factor. So you can find this in the lab menu. All right, so that's task 3. Okay, for task 4, there is we will treat the task 4 as an actual credit. Okay, so again, task 4 will be actual credits for this lab. Let me see. Okay, since we are going to treat this as actual credit, I'm not going to go through the detail for this. But one thing I want to mention is the LM3866 is a power audio amplifier. It is hard to make this work by the AD2 because this chip require a lot of current, which AD2 may not able to provide the current. But if you want, you can still build the filter part. Okay, so this is the filter part. You can still make this work. Okay. Okay. I think that's all for this week. Okay. Any questions?
Can you show the slides, the first slide again for task 1?
Yeah.
So when we calculate the RC and RL,
Yeah.
I mean,
you don't have RL.
oh,
You only have RC. You have task 1, task 2, both are RCs. Okay.
When we calculate RC, we just choose any value that will give us the 23 kilohertz, right?
Yes, but make sure you have those value in your lab kit, like the resistor and capacitor value.
And for task 4, when you say we can just do the filter component, does it mean that we just do the filter and do the network analysis?
You mean task 4 or?
Yeah, task
Yeah,
4.
task 4. So this one, yeah, you don't need to build anything before we amp. Okay, so just build everything after we amp.
Okay.
Yeah.
Yeah.
Okay, you can put we amp as your input and measure the output for this the RSP1 and RSP2. Okay,
And
I
the
think,
output is
yeah,
using the network analysis, right?
yes, yes. So it's not only the output, you need to, the network analyzer will measure both input and output because it need to calculate the ratio of the input and output.
So when we use the network analyzer, do we put channel 1 across the input and channel 2 across the output?
Yes, yes. If you say this, right. So channel 1 is the input and the channel 2 is the output. Okay, any other questions? Okay, if not, I will open the breakout room again if you need one-on-one help. And you can start to do the experiment. And last thing, I saw some students may come late. The next Tuesday we will skip lab 11. Okay, we will do the lab 12. So make sure when you do the pre-lab, you're going to do the pre-lab 12